The current explosion of artificial intelligence relies entirely on a strict, unspoken division of labor behind the scenes. Looking at this matrix, we see the historical rule. Transformers are built exclusively to generate text, and diffusion models exclusively generate images. That division is breaking. Inception Labs Mercury 2 crosses that boundary, using image generation technology to write text. This creates a structural shift in how computers process language. We are moving from analyzing sentences in a strict sequential line to processing massive blocks of text all at once in parallel. By calculating the entire output simultaneously, this parallel approach can generate complete text responses virtually instantaneously. But that extreme speed comes with a hidden cost. Processing language in parallel introduces complex engineering constraints regarding memory and text length that developers have never had to manage before. We are not here to crown a winning architecture. We are going to deconstruct these two distinct engines so you can map the right underlying technology to your exact operational workflow. Let's start with the dominant architecture today. Autoregressive transformers currently power nearly every LLM on the market. An LLM, or large language model, is an AI system trained on vast datasets to understand and generate human language. The core mechanic of a transformer is next token prediction. The model calculates the mathematical probability of what the very next single token should be. A token is a basic unit of data processed by an AI, roughly equivalent to a single word or syllable. This forces the AI to move strictly from left to right. Like a typewriter striking the page, it constructs sentences one piece at a time, incapable of looking ahead to the end of the paragraph. Because they are trained on incomplete sentences and rewarded for guessing the final missing word, transformers are effectively designed to be the world's best autocomplete. The major advantage of this design is open-ended generation. The model does not need to know how long its final answer will be when it starts typing, so it can theoretically generate conversational text indefinitely until it hits a natural stopping point. The major downside to moving one word at a time is a strict physical processing bottleneck. This chart visualizes that sequential speed ceiling. Even the fastest, most highly optimized transformer models generally max out at around 70 to 100 tokens per second. Looking at this logic tree, we see the second limitation, flawed reasoning. If the model makes a mathematical error early, it lacks a backspace key to correct it. That initial mistake compounds moving forward, forcing it to generate permanent hallucinations, false information presented as reality. Transformers offer proven stability and infinite conversational flow, but their left-to-right design guarantees they will inevitably hit a wall when it comes to raw speed and complex self-correcting logic. Now we examine the challenger, text diffusion models like Mercury 2. Rather than guessing the next word in a sequence, this architecture generates the entire required response simultaneously. It starts with a blank canvas completely filled with random noise and meaningless gibberish. Over a series of incredibly fast steps, it iteratively removes that noise. Like a sculptor chipping away excess stone from all sides at once, it refines the whole block simultaneously until a coherent answer appears. Instead of autocomplete, diffusion models are trained on perfect documents that have been intentionally corrupted with random errors. They are rewarded for cleaning up the entire file at once, making them the world's best editor. This results in a massive increase in speed. By bypassing the one-word-at-a-time bottleneck, the model utilizes the full power of your GPU to process every token in parallel. A GPU, or graphics processing unit, is a specialized computer chip designed to accelerate the creation of images and text by performing thousands of calculations simultaneously. This comparative chart shows the performance difference. Text diffusion models can generate over 1,000 tokens per second, making the output feel instantaneous to the user. Seeing the entire output at once grants global reasoning. It can rewrite the beginning of a sentence to align with a planned conclusion. This also creates structural perfection. A diffusion model simultaneously opens a formatting tag at the top and closes it at the bottom, eliminating syntax errors in HTML web pages. But this parallel design has a distinct vulnerability, the length problem. To denoise a full canvas, the system must mathematically predict the total length of the required response before it starts generating a single letter. For massive outputs, like a 2,000-line code file, the model will run out of memory. Developers have to engineer complex systems to process the text in overlapping blocks, a technique called chunking, just to prevent the system from crashing. Text diffusion shatters the traditional speed limit and delivers flawless code formatting, but it requires strict length predictions and heavy memory engineering to function properly. Choosing between the sequential typewriter and the parallel sculptor depend entirely on the specific product you are building. Take a look at this decision matrix for AI implementation, starting with your primary output requirement. First, the open-ended creator. Does your product require natural, conversational text where you don't know exactly how long the final answer will be? If yes, stick with autumn-regressive transformers. For chatbots and creative writing tools, the proven stability and infinite flow of the sequential approach easily outweigh the 100 token per second speed limit. Second, the logic and code implementer. Does your product require structural perfection, strict formatting, or zero latency responses? Latency is the delay between a user's request and the moment the data begins transferring. If your priority is fast, structured data, pivot to text diffusion models. Global reasoning prevents broken syntax, and the instantaneous generation speed is ideal for executing automated background tasks cleanly. However, do not chase the appeal of 1,000 tokens per second if your infrastructure cannot handle the chunking and memory costs required to process large files. The future of artificial intelligence development relies on objective curation. Success comes from perfectly matching an engine's mechanical capabilities to the exact shape of your operational problem.